those. I don't know if this is going to work. We'll just find out. Well, light's still on, so I'm going to assume it's good. Unit 7. Again, Unit 7 was our stoichiometry measure of amounts. So here are our different options. We've got stoichiometry. We talked a lot about limiting and excess. You got a preference as to where we begin this morning. Limiting and excess. All right. Do you want to do calculations with those or practice multiple choice? What do you? All right. First things first. Balance. Yeah. Bam. Oh, man, it's making me thinking it's like 7:15 in the morning. Who's got it? Two iron. Sorry, 4 iron. 4 iron. 6 oxygen. 6 oxygen. What type of reaction is this? Ooh, bonus learning.
Synthesis.
Synthesis. One product. Good. I like it. So if we have 35 moles, we have 35 moles of iron and 35 moles of oxygen, which reactant is going to run out first?
Oh, yeah.
There's mine. I heard a lot of people are just going, I'm just going to wait until the answer is said, and then I'm going to write down the answer. Well, let's think about it. We've got equal amounts of iron and oxygen, but our coefficients tell us that we're using the iron up at a rate of 4 irons for every 3 oxygens. So which one's going to run out first? The iron. The iron. Can I show you?
Yeah.
Can I show you? If we got 35 moles of Fe, 35 moles of O2, can we change them both into iron free oxide? 4-to-2 ratio for every 4 moles of iron. 2 moles of Fe2O3. What does that give you? So if all of our iron reacts, we're going to get 17.5 moles of iron free oxide. Now that's assuming we've got enough oxygen to go with it. So let's do the same thing for oxygen, see how much our oxygen can make. For every 3 moles of O2, we got 2 moles iron free oxide. Right here. 270 divided by 3.
23.
So if all of the oxygen is able to react, it could make this much. The problem is it's going to run out once we make, excuse me, it's not going to, sorry, that was bad. Can I do over, is that okay? The oxygen, if all of it reacts, could make this much of the iron 3 oxide. But once we make this much of the iron 3 oxide, our iron runs out. So we're going to have some leftover oxygen at the end of our reaction. We're not going to be able to get this much because we're going to run out of this before we get there. Thank you for the do-over. Right? If you begin with 80 grams of iron and 60 grams of oxygen, which reaction would you run out of first? Why are we with the noise? The thing. What? Specify for me, please, the thing. Molar mass. The good news is they're elements, so at least you don't have to add, like, glucose together or something. I could have made it like that. Makes up for the do-over, right? because iron may be more massive than oxygen. We can't compare grams to grams. We gotta change them into moles. Mole mass for iron? 55 point.
Sorry, I skipped this.
5.85 grams for every 1 mole of iron. Give us how many moles?
1.4.
4 moles of iron. Oxygen, do we have that one memorized yet? Diatomic, so 32.00 grams for every 1 mole of oxygen. Grams cancel, good moles. Gonna be a little under 2, yes? 1.8 moles? 875? 1.9 then? Technically, sig fig say we should only have 1. Which is, it's the principle. Moles of iron, moles of oxygen. Alright, now I can figure out which one's going to make the least amount of product. Iron, did you do the ratio and plug it in? On the shorthand. Every 4, every 2. Times, so a half be 0.7 moles. Correct? Approximately. 1.4 times 2 divided by 4 is 0.7. Not 0.7? This is iron. For 4 moles of iron.
Yeah.
2 moles of iron
It's
oxide.
0.7, yeah.
Okay.
Confidence there.
For oxygen, we'd have 3 moles for every 2 moles. Sorry, I'm leaking into the problem here just a little bit. So 1.9 times 2 divided by 3, you get 1.3. This one's making excess. We're only going to be able to make this much of our final. It is going to be iron that runs out. Iron that runs out. All right. Alright. Now, theoretical yield, alright. What is theoretical yield? How much you should get in theory, right? Theoretical yield. Alright. So look, it's like fraction on balanced equations as well. From Unit 6. Throwback. Cool. Ooh, and further, what type of reaction is this? We could call it double displacement, absolutely. It is a titration reaction that's happening to our acid and our base here. What do we call that? Say again? There it is. We call this a neutralization reaction, yes? Acid plus base, water and salt, neutralization. Neutralizing each other out. Can we balance it? Somebody's got to commit.
No, because you have 2 O2.
2 oxygen, 2 oxygen, magnesium. Alright. Alright. Suppose you have 45 grams of hydrochloric acid, and you have 45 grams of magnesium hydroxide. Calculate the theoretical yield for both products. Alright. What's the first thing we have to figure out? Sure? Yeah, we gotta find the boss, don't we? We gotta figure out who's in charge of the reaction. We gotta figure out who's gonna limit. Alright. So let's divide and conquer. Let's go this row. And then you two. You guys figure out, and which one do you guys want to solve for? Water or magnesium? Water? Alright. You guys solve for the hydrochloric acid using the HCl 45 grams, how much water you can get. Right? We're going to figure out how much water we can get with the 45 grams of magnesium hydroxide.
Wait, but how do you know that's what
We don't. We're splitting the work. You guys are going to see what it would be for HCl. They're going to see what it would be for magnesium hydroxide. We'll compare them and see which one's actually going.
Okay.
And when you're solving, guys, go all the way to grams. Go all the way to grams of water. Run me through your work real quick.
Okay, so for you have 1.2 moles of, wait, yeah.
What was your mole mass for HCl?
I just put my calculator. I got a 1.2.
Alright.
And then you did the mole train, so for every 2 moles you have 2 moles of H2O.
And for 1 mole of water, we've got
18.016, I think.
yeah. And then what'd you get for your answer?
22 grams.
So theoretically, if all 45 grams of the acid react, we'll get 22 grams of water. Now, we don't know if we're going to get all the acid to react. We got to react that acid with our base. And we got to have enough base to make that happen. I'm going to a baser who can take me through their base work. Not that it's basic. Thank you for humoring me. We have the magnesium hydroxide. All right.
Alright, so I started out with 45 grams of magnesium hydroxide, right? And then 58.326 grams for 1 mole. And then I did the mole ratio, so it was 1 mole of magnesium hydroxide over 2 moles of H2O. And then 1 mole of H2O is 18.016 grams. And then after I rounded to 60, I got 28 grams.
Awesome. So, which of these is the theoretical yield of water? Which one would we actually be able to get? 22 grams. We're only going to be able to get 22 grams because once we've made 22 grams, we're going to be out of our acid and our reaction's going to stop. So here is our first theoretical yield. 2 birds, 1 stone. We found the boss and we found one of our theoretical yields. Bam! Look. But they wanted the theoretical yields for both products. Okay. Well, we know this is going to be excess, so we're not actually going to get that much. Can we use the boss? Because the boss is always in charge. Can we use the boss to solve for our other final product?
You should start with moles.
You could. Absolutely. If you know moles of acid, you can start with moles of acid because you are going to have to do that first step anyway to get back in the moles HCl. Yeah, it's hooked. Hooked. Ratio is to 1 for 2 moles of hydrochloric acid, we will create 1 mole of magnesium chloride. What are we missing?
Are we going back to grams?
We do need to get back to grams, theoretical yield. These are grams. We got more mass for this guy? For every 1 mole of magnesium chloride, we got 95.21. Yeah? Okay. Magnesium chloride, I got confirmation on that? Alright, let's talk science for a second. So this is, in theory, how much magnesium chloride you're going to get, right? Do this reaction, make this much salt. What's the problem with this salt? It's aqueous. So these 59 grams of salt are dissolved in these 22 grams of water, and probably the other water that came with the acids, because these were aqueous, or sorry, our solutions here, they were aqueous as well. So we're pouring our 2 solutions together, they were already dissolved in water. They react, they make more water, and then our salt that they make dissolves into the water. So how would you get the salt back? You would boil the water off. But which product they don't get all used up? Which was our limiting. Our limiting was hydrochloric acid. So you get this magnesium chloride, but wouldn't you also get a little bit of this magnesium hydroxide left over? Ooh. If we really wanted to get just this magnesium chloride, we would probably have to do some form of reaction to get this guy out of the solution so that we could filter and just boil the water off. Because we didn't use all of this, it was the excess. There are leftovers still floating around in our beaker. Sorry, it's just a good theoretical combo to have. Well, how do we do? Ah, nailed it. Love it. Thanks, guys. You're on it. So it's good when the math works out. All right. We guys gotta start with the hard ones first. What next? Multiple choice. Was it have preference left or right? I heard right first.
Good.
Which of these represents the appropriate relationships for the molarity of a solution? This should be pretty quick. Molarity is moles per liters. That would be C. Theoretical yield of reaction is based upon limiting the excess, neither or both. Limiting, final answer? Oh, I did? All right. I did tell you guys started with the hard one first, right? Okay. Based on this chemical equation, if 10 moles of ethane were used with an excess of oxygen, how many moles of water would be produced? Oh, you might have to do a calculation for this multiple choice. We can't just guess. Roman, how did you do that?
Because, well, if it's limiting, then you, in the more number of moles, multiply by 5.
Multiply by 5.
Well, if the ethane is going to control the amount of moles yielded, and you.
So it's 10 moles, and then you multiply by 6 over 2, because there are 6 for water and 2 of ethane, and then you get 30.
Would you agree that for every, I'm just going to reduce, this is a 2 to 6 ratio, which is the same as 1 to 3. For every one of these, we get 3 of these, if you want to think about it that way. So if we've got 10 of these, 10 times 3 gives us 30. If you prefer your mole ratio, you can always plug in your ratio. That's moles of ethane. You know, it's 2 moles of ethane for every 6 moles of water. 10 times 6 is 60. 60 divided by 2 is 30. And if you have 10 moles of ethane and 10 moles of oxygen, which will be your limiting reagent? Oxygen. Final answer? Ba-da-da-da. Sorry, I should be careful if I'm posting this to YouTube. Okay. You can't use anything wrong. Oxygen is, now if you look guys, 2 to 7 ratio, right? For every 2 of these, we use up 7 of our oxygens. So we're using this almost 3 times, a little bit over 3 times faster than our ethane. So if we have equal amounts of both, it's gonna be this one. Anybody remember the shortcut for finding your limiting? If you got moles?
You just divide.
Divide, yeah. Take 10 divided by its coefficient, you get 5. 10 divided by 7, you get
Not 5.
not less than 5?
Yeah. Yeah.
Less than 5. Okay.
Oh. Greater.
No, that's less than.
No, just kidding.
What's the point?
The alligator eats the bigger one.
Right. Good. Now what?
Something easy.
Mass to mass? You good?
Sure.
Okay. Okay. Moles to moles is easier. But mass to mass. If you begin with 55 grams of POCl3, how many grams of chlorine can be produced? You guys give it a shot. I feel like you guys should be able to rock this pretty well.
Thanks.
Yeah, run me through. Meg, give me a burn.
So the bottom is you have to put the molar mass of POCl3, which is 153.32, I think.
153.32?
32. Yeah. And 1 mole. And then you do unknown over known, which is 3 over 2, 3 moles. And then the next one on top, you put the molar mass of Cl2, which is 7.9.
70.9?
Yeah. Over 1 mole. And then when you multiply it out, I got 38.
It's good.
Setup's perfect. See, you were totally right. Why were you worried about the though? It's not like I'm recording it. What? No. I don't know. Like I said, we actually started kind of hard at, and we're working back, layering in those easier ones. Because here we don't have to worry about any limiting or excess. Ooh, what type of reaction is this?
Decomposition. No.
Decomposition. We start with one product, it breaks down into its subsequent pieces, or your divorce reaction, right? Your divorce reaction. Now, why do we end up with Cl2 and O2? They are diatomic elements. Good. They are more stable if they join together in their elemental form with their buddy, with their partner, to be Stable. Good. Another one. Yeah. If you had 65 grams of oxygen, how many grams of phosphorus will also be produced? Hmm?
.97?
Yeah.
Might have been a little high.
So close. It's okay. 65 grams, grams to moles, moles to moles, moles to grams. Plug it in, 2 sig figs. 130. Have confirmation on that?
Mhm.
120. Uh-oh. Uh-oh. What did you, yeah, how'd you, what was the number before rounding? What was your number before you rounded? Did you do the mole step and then do the mole ratio? So it might be you rounded the first time and then you rounded a second time. Might be why you got a slightly different answer there. Whoa, crushing it. Right. Moles. Yeah, look at that. If you are able to produce 2.5 moles of poisonous chlorine gas, how many moles of oxygen would you also produce? Life-saving oxygen. A bunch of people trying to do it in their heads. Ratio is, for 1 mole of oxygen produced, we got 3 moles of chlorine. 2.5 divided by 3.83. 0.83 repeating.
Yeah.
Looks like 2 sig figs. 0.83 moles O2. Nice. If you begin with 75 moles of POCl3, how many moles of phosphorus can you make? What?
Easy.
Oh, nice. Ratio is 2 to 2, which is the same as
1.
1 1. So for whatever amount of moles of POCl3 we have, we get the same number of moles of phosphorus. Nice. What's nice is you guys have gotten more familiar. You're able to see these relationships a lot more clearly just because you're used to working through some of these processes. Remember way back when we first started balancing reactions? It was like, oh, I don't know what to do. And now we've just gotten comfortable enough that we can start to see these patterns, and we found our own method for kind of working through those types of problems. Cool. I think we got one left, yeah? You got 3 moles of POCl3. What mass of oxygen can you produce? I'll throw it at you. Stop yawning. That's okay. It's early. You guys got early coming on Friday.
I know,
You
right?
guys are troopers.
Seniors had to wake up earlier.
That is true.
True.
Oh,
And
yeah,
lunch.
moles. Moles. Guys, if you're getting funky answers, double check your units. I really like to label my moles in my mole ratio. That tells me exactly where they need to go the next step. But question word was what mass? Let me go one more step. Get into grams. What do you get?
I have 48.
40 grams? Nice. If you have 45 grams of chlorine, how many moles of phosphorus can you produce? Ooh, this one's a little different. Reverse. Sorry, am I supposed to be sleeping?
No, don't do that.
Sorry, Chef. 32. Question one was how many moles of phosphorus? I think we're there. Plug it in.
0.42.
0.42 moles of phosphorus. How do you guys feel? Yeah, sorry, let me rephrase. How do you feel upon the chemistry content that we have been reviewing? Tired?
Yeah.
Okay. All right. Let's do this. That's the end of the ones that I'd actually put together. It always kind of varies as to how long it takes to get through some of those problems. So you guys are awesome, divide and conquering, work through those example problems. At this point, I'm kind of thinking I'm just going to open the floor to you guys. If you have any questions, it can be from first semester, second semester, whatever items you may want to review. We can have this be your time to do that.
Okay. Can we review electron configuration?
Absolutely. Like what part? Is there a part specific you want to review on electron configuration?
Yeah.
Or
On the study guide, it asks what is the electron configuration for an atom of
chlorine?
chlorine?
Oh, this is
I'm not-
long.
It's been such a long time since we made electron configuration. Yeah. Okay. I would start with pen numbers, guys. All right. I know it doesn't work. Didn't fit. I'll probably get in trouble for putting that on video too.
Yeah.
Protons for chlorine.
Oh, wait, I got
For
17.
17 protons. All right. If this is a neutral atom of chlorine and we've got 17 protons, how many electrons? Have to balance out those charges. For every positive, we need to have a negative. Now, if, let's just say, for the sake of our example here, it's chlorine 35, total mass of 35, and if we have 17 protons, how many neutrons would we have? 18. What'd you do? Subtract. 35 by 17 gets us our other mass particle, 18 neutrons. How are we doing pen numbers? That's the unit 2 throwback.
Crazy.
What's the 1s2 2s?
That is our electron configuration. Yep, that's what we're going to do. Yep, so to do an electron configuration, remember, it's an address. We're describing the general location of where we can find the electrons. And we got 4 parts for our address. When we do electron configurations, we're really looking at the first 3 parts. The energy level, the sublevel, and the number of electrons in there. So, the reason why I started here was because if we're going to do an electron address, we kind of need to know how many electrons are in there. So we need an address for these 17 electrons. Good old Aufbau principle. Aufbau, which is German for building up. Aufbau says that electrons they have set shells. And our electrons, if we're building up, they're lazy. They always go from the lowest energy and work their way out. So we have a set pattern when we start filling because we always Start at the lowest energy level. Well, what's the first energy level to get filled? Energy level 1. In the first energy level, you can have one sublevel. The first sublevel is S. What shape did the orbitals take for the S sublevel? S for sphere. And in that sphere, we can put how many electrons? 2 electrons. 1s, 2. Well, we've got 2 in a home. We're not quite there, though. Our first energy level is full. We go to second energy level. 2s, 2. In the second energy level, we can have an S sublevel. We can also have a P sublevel. How many can we put in P? 6 electrons. What shape did the orbitals take in the P sublevel? P peanut. Good. Looks like we've used 10 electrons, yes? How many left? 7. Well, do we have any more room in the second energy level? Oh, no room in the in? Go to the next one. Next shell is 3 energy level. We got 3s. You can put 2 in there. We've got 10, 11, 12. We've got 5 left. 3p5.
And then when is it that it starts skipping?
Okay.
That's when.
If we were to look at, say, titanium. How many electrons for a neutral atom of titanium? 22 electrons? You okay on that part?
Yeah.
If you assume it's neutral, we got 22 protons. They're in 22 electrons. The pattern for our filling is always the same according to Aufbau. 1s2, 2s2, 2p6, there's 10. 3s2, 3p6, there's 8. So we're at 18. We've got how many more? Got 4 more, yes? Now here's where that skip comes. Before we fill the 3D, we fill 4s. And this comes back to the energy required. It takes less energy to make one sphere than it does to make 5 double peanuts. It's kind of a zipper effect. So our 4s, another 10, will fill before our D. And we need 3D, 2, I believe, to make the mistake.
Wait, but then wouldn't, like, if you're on 2p6, wouldn't it go to 3s2 before 2p6?
Nope, it's just for the D's that we see that overlap, not for the P's. SP, SP, but before the D, put the S in. Nope, we did not get that. The only elements that are large enough to require the F block are lanthanide and actinide series there at the bottom of the periodic table. Those are radioactive elements that we've just kind of started introducing this last week here. But we've never written the electron configuration for those. We could do it.
No.
That's
This is probably a weird question, but on nuclear chemistry, the pin numbers are the same as the pin numbers earlier, right? Okay.
The only pieces we're specifically writing, instead of writing it kind of as its mass number here, we've been writing it in its nuclear symbol.
Okay.
But yeah, they're the same. Yep. It's like what we're doing reviews, what we learned. Oh, I love it.
If we feel like we know, or we don't have any questions, can we leave early?
Yeah. Yeah, this is totally like this is meant to be. Good.
Are we gonna be given the? Oh wait. Are we gonna be given the R value?
Yes. Yeah.
Can we go over like the sharing electron, like covalent ionic?
Sure.
Like, what?
Hot unit 4. I don't know. I like it. So you want to talk about like the different the types of bonds? Is that
Well, like I know like the type of bonds, just like sharing electrons or.
sharing equally, unequally, that sort of stuff? Like 3. Let's do the 4 bond types. We've got covalent, ionic, metallic.
Yeah.
Is that what you mean?
Yeah.
I want to get your question in.
That there was like, I don't know, there was questions on the study guide that was like, which of these like shares electrons. I know like what they're between like metal, non-metal. I just don't know.
Okay, well let's layer that part in first. Covalence between what types of atoms?
Two non-metals.
2 nonmetals. Ionic is between
One metal and one non-metal.
metal and non-metal. Metallic.
Two metals.
Okay, there.
I got this.
Now there's two types of covalent sharing. If we think about a covalent bonds are the result between two nonmetals. When you look at your nonmetals on the periodic table, you'll notice up there by fluorine we have high electronegativities, yes? Remember electronegativity is the attraction for electrons in a bond. If we look, since we're closer towards the right, that means we got lots of protons in our nucleus. Because we got lots of protons, we're good at attracting more electrons. So if we attract more electrons, we have a higher electronegativity. We hold on to pull those electrons more. So because we're between nonmetals, they all want their electrons. They don't give them away freely. So what we end up seeing here is instead of a transfer, we see a sharing of the electrons. So covalent bonds is a sharing of electrons. There's two ways you can share. For all of those who have siblings, what are those two ways you can share? Equally, or more often than not, non-equally. We have two types of sharing. If we share equally, we're said to be non-polar. Right? If you share equally, you both are happy, everybody's a winner, right? If you share unequally and your younger sibling gets that toy more often than you do, they get really happy, you get really angry, and we have what we call poles. So here is a non-equal sharing results in our polar covalent bond. Polar covalent bond. Okay. Whoever pulls those electrons closer to them becomes a little bit more negative. The person who has the electrons further away from them becomes a little bit more positive. Okay. This is the result, equal sharing, guys, between two nonmetals that are identical. For example, your diatomic elements. You know, bromine is a diatomic element, Haas-Brinkel. The electrons in between here are being shared equally because they have the identical electronegativities. This bromine has the same attraction as this bromine. If we were to switch it to something with two different electronegativities, fluorine being more electronegative, pulls those electrons closer, it becomes a little bit negative, hydrogen N becomes a little bit positive. You get our polar bond.
Is that how you do like two double bonds to figure out which
Lewis structures, it's a little bit different. Lewis structures a little bit different. Did that answer your question about the sharing in the polar non-polar? Ionic, we see a complete transfer of electrons. For example, our sodium will give its one electron away to our chlorine. And when it does that, the chlorine becomes fully negative, the sodium becomes fully positive. It's these attractions that stick them together. What happens to your electrons? So here we've got transfer electrons. What type of electrons in a metallic bond? Delocalized.
Did we make like a chart or something with what it means? We should have
Cool. You want to draw some Lewis structures? Is that next request?
Yeah, sure.
And you want one with double bonds?
We'll
Yes.
those for double bonds.
When you're drawing Lewis structures, what's your first step? Got your total number of valence electrons. We got two nitrogens. Each nitrogen has how many valence electrons? 5. They're in the fifth column, so we've got 5 plus 5. We got a total of 10 electrons. First step, count up your electrons. They're our glue that we're going to use to stick it together. Now we need to pick a central atom. What do you want to put in the middle? Good old nitrogen. All right. Okay, pick a center atom. Next step, bond it to your outer atoms using a single bond. Now, how many electrons are in a single bond? 2. So we've used 2. We've got how many left? All right. Use your remaining electrons to fill your outer atom's octet. Right now, this nitrogen has how many?
One.
The way we have it drawn, it's got 2 being shared with it, so it needs how many more? 1, 2, 3, 4, 5, 6. We just used 6. We've got 2 left. Leftovers go where? On the other nitrogen. If we look, we have used all of our dots. We used all 10 electrons. 2, 4, 6, 8, 10. But it's not even. Is this nitrogen stable? No. So if we run short, what do we do? We make double bonds. We're going to do a little extra sharing. Here you go, buddy. These electrons come down, form a double bond. This nitrogen still has got 8 around it. This nitrogen gets the added benefit of having 2 more to it, so it's got 6. Stable yet? Sorry, you got bonus. Not a double bond, but
Triple bond.
triple bond. What shape would this be? What's the only shape that 2 atoms, when joined together, can make? Linear. Yeah, it should be linear.
Was that gonna be on the test too?
Shapes, maybe. Anything's free game.
Wait, so how do you know which atom to start with?
Here we had either nitrogen or nitrogen. If you have carbon, usually we'll start with carbon. We want to use the one, whichever one makes the most bonds. Whichever one will make the most bonds. Cool. Oh, done?
How about looking at it, yeah, that was.
Oh, yeah. So we got like something like this. If you find carbon on the periodic table, how many valence electrons does carbon have? 4. How many more does it need to become stable? 4. So how many bonds will it make? 4. Yep. If you look at nitrogen, let's say you had NH3. How many valence electrons does nitrogen have? 5. How many is it missing? 3. So how many bonds will it make?
Oh, so how many is missing is how many are there?
I'm going to stop the recorder. Okay. If you guys have any individual questions, we'll be more than happy to come around and take them. Thank you for your time this morning, guys.
Thank you.
Absolutely.